Hello, everyone. I am Wang Junliang from Scantech. I am delighted to share my thoughts on handheld 3D scanners with you. Today, the topic is 3D laser scanning technology empowers high-end equipment manufacturing. The presentation consists of 4 parts: castings and forgings inspection, mold manufacturing, product maintenance and aftermarket. These are also the main phases of industrial manufacturing. First, let's talk about how 3D scanners are applied in casting and forging. There is a long history of casting and forging, which can date back to thousands of years ago. Here, I will discuss 4 aspects of the inspection. Inspection of the cast and forged parts. Allowance analysis. Delivering the inspection results to the manufacturing equipment. The last is the optimization of the design of casting mold and forged die. As you can see, there is a picture of a wood model being scanned. The casting and forging molds are usually huge. I used to see a mold longer than 10 meters. It is challenging to inspect these large-scale molds. We recommend handheld 3D scanners for measuring. From the picture, we can see the technician was using a 3D scanner to measure the part. The mold is large, and it is hard to transport it to a measuring lab. With a 3D scanner, we conducted an on-site 3D scanning of it and obtained its point clouds. We then compared the data with a nominal CAD model and obtained a color map. The picture next to the wood mold is a color map. The green areas in the map mean deviations are within the desired range. The warm colors such as yellow and red and cool colors such as blue represent that deviations are outside the desired range. It is very convenient to identify these deviations to correct these molds. The molds come in different types: lost foam mold, wood mold, sand core mold and metal mold. 3D scanning suits well for these molds. Now, I'll show you some examples of how 3D scanning is used in mold inspection. Allowance analysis is the basis of the measurement of the cast and forged parts. When a forged part is manufactured, we should identify if there are sufficient or insufficient allowances on the pre-machined surfaces. Then, we need to check whether there is a uniform allowance distribution on non-machined surfaces. The key to precision machining is to adjust the coordinate system of the blank. In some cases, the blank can't be precisely machined with traditional ways. However, with 3D scanning, we can inspect it more accurately to get the change to adjust its coordinate system and machine it. How to machine the blank? We need to obtain the datum for the tool setting. I've listed a few of them here. Traditional line drawing. Technicians draw lines on the cast part, and the lines serve as a datum. The machining center then uses these lines to machine the part. Second, auxiliary tooling. Then, the robot-assisted method. The robot markers the part and delivers the information to the manufacturing centers. Another way is to align the scanned data with the equipment of machining centers. Adjust them to the same coordinate system so that the blank can be applied to the center directly. Delivering the inspection results to a center for machining is one of the hot topics in the industry. A large number of companies have devoted themselves in researching it. We have done a lot of researches on this and completed a lot of projects. If you're interested in this, you are welcome to talk it with us. Now, let's take a closer look at the casting and forging measurement characteristics. The first feature is large size. The second is curve measurement, and the last is datum for tool setting. So let's look at 2 cases. The first is the inspection of a large-scale wind power hub with curved surfaces. The ordinary 3D scanner aligns scans with markers. When it comes to 3D scanning this huge part, alignment by the marker is insufficient to obtain precise results. Its alignment errors accumulate over the distance of measurement. There is a particular technique called photogrammetry, which suits well for wide-range measuring. It can take pictures from different angles with coded markers to obtain 3D coordinates. Scantech offers a composite 3D scanner that combines scanning with built-in photogrammetry. The 3D scanner features two light sources, blue lasers and infrared lasers. When 3D scanning a huge boss wheel, we can use an infrared laser for rapid scanning. The second case is a mold that features deep grooves. 3D scanners project lasers onto the surface of a part, and its two cameras is used to capture lasers reflected. These two cameras have to see lasers at the same time. The camera distance of ordinary 3D scanners is relatively long and it is hard for them to capture details in grooves. We have a compact 3D scanner SimScan that is specially designed for it. The distance between its two cameras is much shorter, and the angle between the two cameras is relatively small, making it convenient for scanning deep grooves. Now, let's move to the second part, mold manufacturing. Mold is known as the mother of industry. It is a piece of important equipment in product manufacturing. A part that is newly cast will be sent to the machining center. The first task is the inspection of the rough part. We need to check its allowance. Its allowance may be sufficient for machining, but it may be non-uniform over the surface. There may be 20 mm allowances on one area and 2 mm allowances on another area. If we refer to a CAD model to set the machining program, we may face the challenge that the machine fails to eliminate the metal layers thinner than preset parameters. Therefore, we waste time processing. 3D scanners can obtain the accurate data on the blank and adjust the machining equipment by setting the program precisely. The processing path can be optimized in this way and increase machining efficiency. What else can we do? We can scan the mold machined and compare it to the CAD model to generate a report. The color map report can tell deviations intuitively. Green means qualification and red means disqualification. We can even get the specific values of deviations. Here is another example, which is assembling analysis. When the mold is manufactured, we must check whether the punch matches the die by assembling them. Check the interference or gap. Our 3D scanner can scan the die and punch fully and virtually assemble them on the computer to analyze it quickly. It's also a meaningful way to improve efficiency. The in-service molds are subject to wear and tear. So, we need to repair them. Our 3D scanners can scan the mold and compare it to the original model to identify areas to be repaired precisely. During the repair, there are many versions of changes. We can record these changes digitally by scanning parts and storing them digitally. It is very convenient. Next, we'll talk about manufacturing. 3D scanners are widely used in this industry. Let's take the automobile industry as an example and look at the process of producing automobile. For example, the assembly of the engine stamping parts and the subassembly. There are interior and exterior piping, lights, tires, boss wheel, seats, and glasses. As long as the dimension is involved, 3D scanner is needed. We can use 3D scanners to analyze the dimensions. Besides the manufacturing, another application is product maintenance and aftermarket. The maintenance part of the product is a process of remanufacturing. It is an emerging industry. Product maintenance includes product repair and remanufacturing. The remanufacturing uses technical methods to repair and transform waste products based on the original sector. The picture on the left is of a broken-down engineering machine, and some of its shafts were broken. Or we can say the shaft was deformed and required repair. There is no drawing available, so we need to scan it first. After analysis, we can provide guidance for the remanufacturing. The picture on the right is the scanning and analysis of a part for repair. Remanufacturing industry is still in its infancy, whose development can be accelerated with 3D scanners. Another application of the product aftermarket is customization. Customization is proliferating as the living standard improves. For example, caravan customization, pipe customization, and paint protection film. Our 3D scanners can obtain the dimensions of parts and conduct various tasks. Therefore, we can be confident in saying that 3D scanners can be widely applied for customization. And that brings us to an end. Thank you so much for your interest and attention.
Hello everyone, welcome to Scantech live streaming. I'm Harris from the Innovative Applications Department. Today, my topic is how to utilize 3D digitization technology to empower 3D printing. Scantech is one of the earliest high-tech companies starting to research and develop handheld 3D visual measurement devices worldwide. Our product line ranges from metrology-grade online and offline equipment to consumer-grade color 3D scanners. Scantech's 3D scanners are widely used for metrology in industries such as aerospace, automotive/rail transportation, machinery manufacturing, and so on. Besides that, we are working hard to improve our in-house 3D digitization technology. Combining 3D scanning and 3D printing is one of our core research areas. Then, I'll introduce you to 9 aspects of 3D digitization technology, how we utilize 3D digitization technology to empower the 3D printing industry. The first aspect, quality builds the future. 3D printing requires high-end tech and strict quality control. As long as there's product manufacturing, quality inspection is required. Here, at Scantech, we offer mature solutions for automated batch inspections. The industrial-grade laser 3D scanner we use has a maximum accuracy of 0.025 mm, which can meet the inspection requirements for most 3D printed parts. As we can see in the video, we can automatically generate a color map by scanning a 3D printed part with a 3D laser scanner and compare it with the original CAD model. In this way, we can tell if it is qualified or not at a glance. Besides, we can preset the comparison templates according to the inspection requirements to inspect items such as section deviation, center distance, contour, flatness, center coordinates, etc. Each part is automatically detected one by one according to the templates with automatically generated inspection report. This fast and comprehensive inspection method can be used in 2 aspects. One is to scan the finished 3D printed parts, compare them with the standard drawings, analyze the quality of 3D printed parts, evaluate the stability of the 3D printing and generate an inspection report. It ensures end users to provide high-quality 3D printed products. The other one is to use it to detect and compare different parts in the same batch or different batches, analyze the stability of 3D printers, and assist in the research and development of 3D printers with more stable production performance. We have successfully implemented this high-precision detection method in additive manufacturing technologies such as SLA 3D printing, wax 3D printing, metal 3D printing, and nylon 3D printing. Leading companies in 3D printing in China including Shanghai TPM 3D, Shanghai UnionTech, Beijing Longyuan AFS, have used our 3D laser scanners for daily production inspection or supplying our products to their customers, providing complete product delivery solutions. The second aspect is reverse design and smart restoration. One of our partners adopts 3D laser scanning technology to offer customers smart laser automatic repair solutions. This video demonstrates how to obtain 3D data of unrepaired parts by a 3D laser scanner, reversely acquire high-precision 3D models of the damaged parts by third-party design software, and automatically restore the parts by programming and path planning. The integration of the 2 technologies can help the manufacturing industry perform better.